So they have the same surface area, right? Because they're both made from one sheet of paper. Okay. Okay, so if we go back, what we did with this here, we're supposed to cut them out so that we had, this guy's 5.5 tall, but then its perimeter around the base is 8.5 and 8.5 and 8.5 and 8.5. So with this guy here, which one has more volume?
They both have the same volume.
Do they have the same volume? Here's one, right?
I got the short prism with the most volume.
So if you do this and you cut it in half and then put this piece down in here, you only have half of it. So this is half of the volume of this. Do you see that? Even though it's got the same surface area, the volume is dramatically different because you have a shape like this. You just imagine, what if you took this piece of paper here and you cut it into a bunch of narrow strips and you made it big and long and skinny like a pencil, like a piece of spaghetti. You'd have a tiny, tiny volume and all kinds of surface. It's like if you put noodles in the water. Spaghetti boils up and softens fast. But if you put those big lasagna noodles, those big thick ones, they don't have a lot of surface area. So they gotta be boiled longer. So let's see, where are we at? We have to calculate the length of the sides of the base of the tall prism. And let's see. I feel like I'm missing something. So the tall skinny box has more volume. The tall, or the short wide box has more volume, or both boxes have the same. So we decided that the short one has more. That's step 3. So now test your conjecture by using the formula volume is equal to side squared times h for the volume V of a box with a height h and a square base whose sides have length s. So that's what that means. If we say we have the volume is equal to the side length squared times h. Basically what we're saying is this. If this is a side length and this is a side length, and then this is the height. If we think of volume as length times width times height, it's length times width, which is side times side, so this is a square base times the height. So that's the volume right here. So calculate the length of the sides of the base of the tall prism. So what are the lengths of the sides for this one? How long are each of these edges on the base? How much are they? 2.125?
That sounds right.
Is that right? 2.125 inches. That's 2 1/8, right? 1.125, so that's 2 1/8 inches. So 2, 4, 6, 8, and 4/8 is 8.5. Okay, that makes sense. What's the height of this one? It's 11 inches. Okay, so if we plug these numbers into this, what do you get for a volume? For a volume, what did you get, Trenton, you started saying?
Yeah, I got 48.51.
48 point what?
51.
Point.
Yeah, 0.51.
Is there more to it than that?
There is, but I didn't add 0.125. I did 2.
Well, let's put the whole thing down, just for fun of it. What do you end up with? Or do you want me to do it? You got 2.125. Ooh. No, I don't know what I got there. I don't know what I did. I got the wrong thing. What do you have? Oh, you got 49.67.
Yeah, if I put the entire thing.
So you got 49, you said 6.7?
Yeah, 0.67.
Okay. So it's about though, isn't it? Because there's more place values?
Yeah.
Okay. So then, do the same thing for the short prism. Okay, so this is for the tall one. So what's the side length of this one? What was the side length of that prism?
Side.
Yeah, so the side of the base.
Side, like this.
Yeah, this one right here.
Which one of those should be?
4.25, right?
Is it 4 1/4?
Yep.
Because it'd be 8 1/2 across, and then we cut that in half with a fold, so we have 4 1/4. So we're gonna square 4 1/4. And then how tall is this?
5.5.
Yeah, that's half of the 11, so it's 5 1/2. So what do you get for that volume?
99.34.
Ooh, okay. So this is square inches. Should probably include units on that. So it looks like it's like twice the volume, isn't it? You get twice the volume from this than you have from this. And I think it is, like, I think you can find that it is exactly twice as big. And you can kind of see that if you put this one in.
49.67.
Yeah, 0.67 is what that comes out to. But if you put this, the narrow one in here, it's definitely twice as tall as the short one, because we tore the paper that way. And because of the way we folded the paper, here are 4 folds, here are 2 folds. It's definitely half of the base size. So you ought to be able to take one of these and cut it in half and fill in half of this. And then you ought to be able to take 2 of these, cut in half, and fill in the whole thing. So I think that the relationship between the two is exactly twice. This is twice the volume of this. So if you were in business making boxes, and you wanted to make a box that would fit the most goods inside of it, compared to how much material it takes to make the box, which of these would be better? Short, squatty one, yeah. This has less surface, it's gonna take less cardboard to make and hold just as much as this. So if you're, now it all depends upon what you're packing. If you're packing spaghetti, that might not work. But if you're packing little round noodles, little shells, this might be a better box than this. If you're doing things like water or soda or something like that, this kind of a shape is gonna be better than this. So like Red Bull cans, very inefficient. You're paying a lot of money for aluminum. Whereas a regular soda can is closer to this, but it's still made so it fits in your hand. So that's something that goes into design and engineering. I mean, after all, what's the most expensive part of a can of soda?
The shipping.
The shipping is way up there, but even more than the shipping is the aluminum. So if you can make it with less aluminum, the better.
Bottles.
What's that?
Bottle.
Bottles? And reuse them?
Are they expensive, like aluminum?
Bottles are pretty cheap. What's expensive with bottles is if you use refillable bottles, shipping them back. You know, like for us, it'd be ridiculously expensive because they don't have like a Coke or a Pepsi manufacturing facility in Juneau. Our stuff all comes up from Seattle, so somewhere down in that area, they've got bottling plants. And to send bottles back down there would be really, really expensive. So, but back when I was your age, most soda could be bought in returnable bottles. So you buy a case of it, and then you pay a deposit. Usually it was $1, and beer was the same way. You could buy a case of beer, and it came in this reusable box. There were 24 bottles in there. And for soda, it was the same way. It was a reusable box for kind of like a flat, like these kinds of boxes that we have up here for our stuff. But it'd be divided and partitioned. And you put your bottles in that, and they would, some of them were even wooden. And you would just, you drink your soda, put the bottle back in there, and then you would take your case back. In the very first case, you'd pay $1 for a deposit for the whole thing. But then every time you'd go back to get more soda or for more beer, you would just bring it back to the store, and you'd say, here's my empty, and then you wouldn't pay another deposit on it. And they would take all those empties, and they would take them back, and they would wash them and reuse the bottles again and cap them. They didn't have screw caps. You had to use a bottle opener of some sort. But it just started becoming so expensive to do that. More expensive because things like plastic are really, really inexpensive. And the reason that they are inexpensive is because we consume so much gasoline, and plastics get made from crude oil. And when you use all of this gasoline, they have the other parts of the crude oil that are left over, and it's like, what do we do with it now? Well, it turns out that it's very inexpensive. Compared to how much money they make from the gas, it's very inexpensive for them to make plastics. And that's why we have so many plastics and end up with so much waste from plastic, because it's dirt cheap to make this stuff. When I was your age, plastic was first starting to become popular. I can remember when I was a little kid and there really wasn't plastic. I remember when Saran wrap came out. Think about that. We didn't have it back in the day. We just used aluminum foil. And before aluminum foil, they used what's called tin foil. But tin started getting more expensive, aluminum started getting cheaper. And aluminum is more bendable, it's more what they call malleable. So it seals up a little bit nicer than tin did. So, yeah, anyway. All from a couple pieces of paper like this. So let's look at this a little bit differently now. In example number 4, they say that the tall box has a particular volume, and that's the side length here. So I want to change my drawing so that maybe we can recognize all of these things. I'm going to draw a tall, skinny box. Let's see, let's do it this way. Okay, so then here's our tall, skinny box. And the footprint of this here is S and S, and there's the height. And then our short, squatty box is like this, more so. Okay, so here's the short, squatty box, which again has an S and an S and an H. But these S values are different, aren't they? This one here, this is 2 1/8. And that comes from taking our sheet of paper, which is 8.5 inches, and dividing it into fourths. When we took that and we folded it around. So we bent our paper, we folded our paper like this, increased it. And then our height here was 11. But now with this box here, I want to change how we label these variables a little bit. So here we took 2 1/8 times 2 1/8 times a height of 11. So we took 2, I'm going to write it like this. And that was equal to our volume. But with this one here, this S and S, they weren't 2 1/8, they're 4 1/4 inches. Because what we did with this paper here is the paper started out as 8.5 inches wide, like this, again, 8.5. but we divided the paper after we cut it in half. So we took this total height here, and then we said that this much is height divided by 2, or 1/2 of the height. And then going across the bottom, we called this 4 1/4. And this is 4 1/4. Instead of 2 1/8. So what we can do is we can kind of change the way we wrote these formulas. This tall box here uses that 2 1/8. And that 2 1/8 is 1/4 of this side of the piece of paper. Whereas this here, this 4 1/4 is half of this side of the piece of paper. The tall narrow box uses the whole length for its height, but this just uses half of that long piece of paper for its height. So what we're doing is we're kind of manipulating and changing the variables that we use for finding the volume. And what we're going to do is we're going to try to write one relationship that compares both of these formulas, but more realistically. Because here we just said it's side times height, side times height, which is fine. But that side is related to this side, because this is half as long as this. And the height, well, this height is half of that height. So if we really want to write these formulas using the same variables, we have to consider that if this is a whole h, this is only half of an h. And if this here is half of the width, well, this is only going to be 1/4 of the width, which is going to be a little bit different as we write it. So here's what they do. They go and they rewrite these formulas, and they say the volume of, they start with the tall box. So I'm going to say V sub tall. So that just means the volume of the tall box. And what they do is they rewrite this side length here. And what they do is they say that that is equal to just 1/4 of this entire length. And if you look at this entire length, it goes all the way around, and that's the same as the perimeter. So where do my boxes go? Here. So the bottom of this box has a perimeter that goes all the way around, which is this long, 8.5 inches. Each side is just 1/4 of that. So P over 4 is this side length, and we squared it, and then we multiplied it by the height. So here's a different formula, and now we can write a second formula for the square box, or it's more square, I don't know, what do you want to call it? Short, I guess. We'll just say it's shorter. So the short box, instead of taking this piece of paper like this and dividing it into 1/4 to get one edge, we took this piece of paper and we cut it in half. So we have P over 2. This is only half of the length of the paper that goes all the way around the bottom. We call that all the way around the bottom of the perimeter. So we take that and we square it, but then we don't multiply it by the height here. We multiply it by this height. This is probably the most complex algebraic manipulation we've done so far. So what are your questions now on that? Because going forward, we need to have somewhat of an understanding of this, of what we did. Would you like me to back up? Go over the whole thing smooth and once through? Was that a nod? You want me to go back over it again? Yeah? Okay. So we took a box and there's a little piece of paper. So if you call this side length here the perimeter of my box, perimeter is the distance around. So what I did is I folded the thing up. You did this too. You folded up your box. So that that perimeter got cut into fourths. And that goes around like so. So now each side of this rectangular shape is 1/4 of the whole length. So this gets folded up into this shape. So all of that across is P. But this is 1/4 of P, as is each of these. So we just write that as P over 4, because P over 4 is the same as 1/4 times P. So that was this side length here. We took that times itself, then times the height. But in making this box, we left the whole height of the paper, we left it intact, and that ended up being 11 inches. So side length times height. Side length times itself times height. That's the volume of the tall box. But then the short squatty box was made by taking that same piece of paper, cutting in half like this, taking those two halves, taping them together, and then squaring it up to make a box like this. So now what you did is you took this length here, took a piece off, brought it down here, and you made your sides 4 1/4 inches long, only half of this 8.5 inch width. So we took half of that 8.5 inch, we divide by 2, and that's your side length here. So that times itself, times the height is the volume, but the height is not 11 any longer, the height is only half as tall, because when we tore our paper in half, we only have half as tall of a box. So when we did all of the arithmetic here, we found this to be 49.67. Can I say about 50? Let's say that this is about 50. And then when we did all of the arithmetic here, we found that the short box was about 100. So this one's twice the volume of this one. So this number here should be 2 times as big as this. So here's what we're going to do. We're going to figure that out. Is this number 2 times as big as this number? So how can you compare to see if they're equal or not? Or if one is bigger than the other? What could you do to those equations? You could substitute numbers in. We did that already. But this is algebra. And in algebra, we want to do things with variables, because then we know it will work for any box that we make, not just this one. Because you might say, well, yeah, you proved that it works for this, but what if I had a really big piece of paper? Does it work for that again?
Yeah.
Prove it. How would, no, not by doing it with a piece of paper. Because then Griffin, what you'd have to do is you'd have to do it for every single possible size of paper. And that's what algebra does. algebra does this for every possible size if we use variables. See, we don't have any numbers for width and height, do we? We just have P and H. And our piece of paper that we started out with is P wide and H tall. And we wrote everything in terms of that P and that H. So if you had a piece of paper that was 12 by 24, or if it was 1 by 2, any size whatsoever, if we can prove it with variables, we've proved it for everything. So how do you find out how these two relate to each other? Remove the parentheses. Okay, so now here we are, we're to the power of a quotient. The 2 goes with the P and the 4. And that's times H. So now what is 4 times 4?
16.
Okay, so I've got P times H over 16.
Doesn't the P stay squared too?
Whoops, thank you, P squared H. And that's written half baked. No, it isn't, that's how I want it to be, because this is a lowercase p. Either way, so that's P squared over H. Or P squared times H over 16. So this one here, we're gonna do the same thing. We've got P squared over 2 squared times H over 2. This one's gonna take a little bit more work. So we've got P squared times H. 2 squared is 4 times 2 is 8. Okay, so this is P squared, this side, P squared H over 8. So is this number 2 times as big as this?
No. Or yes.
So in other words, if I took and I multiplied the one on the left by 2, will it then be equal to this? Well, this is 2 over 1. 2 over 16 equals 1 over 8. Isn't that what this is? So we just double that one, it's equal to this. If you double the volume of the tall box, it's equal to the volume of the short box. Always, every single time, if this is how we divide up our sides of a piece of cardboard or paper. All right. You guys remember ratios and proportions? Yeah. If you say something like this, a half is equal to 2/4. Well, 2 times 2 is equal to 1 times 4. When you cross multiply to find out if they're equal, well, watch this. We've got P squared H over 16, and then we've got P squared H over 8. So if I multiply, I got 16 P squared H, and then on this side, I have 8 P squared H. So what I did is just cross multiplied. Now, if I was to divide each of these by 8, then this is 2 times P squared H, and this is P squared H. So this shows us also that I would have to take 2 of these to get 1 of those. That would be the only way it would be able to be equal. So you can think of this in ratios and proportions as well. That's as far as I'm going on that. But this is kind of the beginning of algebra stuff now. We're starting to get there because we're starting to give you enough tools to be able to work with things. So, your homework on all of this. What do we need to finish? Did we start? I think we started, right? This thing is dragged out for a while. But my goal is for you guys, for what you're able to do, that you're able to do it well. That's really what I want. Did you do 1 through 7 or something?
1
Or 1 through 9, there you go. So 1 through 9. So what I need to get out of you through and through is through number 19. And then I'd like you to take a look at 20 and 21 also.
On 485, starting with 485.
Yeah, 485, yes. So get it done all the way through number 21. Kind of look on page 486. They've got something there with an index card. And I think while you guys get started with this, I want to run and grab you some index cards so that you can kind of picture what this is all about. Because this can be number 12 can be a tough problem to picture. It's similar to this idea, except it has to do with the cylinder. So I'll run and grab those. Index card will be very